In this video, let's introduce an important concept in discrete mathematics, the pigeonhole principle, which states that if k is a positive integer and k plus 1 or more objects are placed into k boxes, then there is at least one box containing two or more of the objects. Say, for example, in this box. So we have 4 by 3, so 12 compartments, but we have how many pigeons? We have 13. 1, 2, 3, 4, 5, 6, 13. So that means one of the box will contain at least two, so two or more pigeons in that case. Now it's not necessarily full like this, so this is just an example. So this is not the requirement that it should be full, because as in the first case, 3 pigeons are in one compartment and 2 pigeons are also in another compartment, or there could be more in various compartments like the third example. So with this visualization, we could clarify the statement further. So here, suppose that m objects are distributed into n bins. We want to prove if m is greater than n, then some bin contains at least 2 objects. Or what is the contrapositive of this statement? That means if every bin contains at most one object, then m is less than or equal to n. Perhaps we could state this a bit more formal. Say, if you have the cardinality of set A is basically greater than the cardinality of your set B, then it implies that a one-to-one function from A to B or from set A to B does not exist. Okay, so we have now this P proposition, then this is now our Q proposition. So we can prove this by contradiction. So for example, the contradiction of the implication, so not of P implying Q, is equals to or equivalent to, they are not equal, so is equivalent to the not of P, negation of not of P or Q, or that is P by De Morgan's, and not of Q. Hence, we could, if we are going to prove by contradiction, then our assumption will be cardinality of set A greater than cardinality of set B. And so there exists a one-to-one function from A to B. So there exists A to, so I'll just use to B. Now, so after assuming this, we should somehow show any contradiction. For us to prove the original statement. So let's add more space there. For us to show a contradiction, then we have to somehow manipulate this idea that there is a one-to-one function from A to B. So how do we play with this idea? Basically, if we are going to think about it, if this is set A to set B, if we are talking about a function, a one-to-one function, say for example you have maybe set A will be composed of A or letters, for example. So this will be A, B, C. And for set B, for example, it will be composed of numbers 1, 2, 3, 4, for example. For us to have a one-to-one function, one-to-one mappings, then it is basically, as you can maybe visualize, then the cardinality of set A for a one-to-one function to exist, the cardinality of set A should be less than or equal to B. And this can easily be illustrated when, for example, we have a cardinality that is greater than set B. So for example, if I have more elements here, say I have D and I have an E. So in this case, the cardinality now of A is 5, and 5 now became greater than the cardinality of B, which is in this case 4. So in that instance, you can see that if you assign D, you could assign it to 4. After that, the E cannot be assigned without duplicating the assignment from the previous domain elements. So if you're going to assign this to either 1, 2, 3, or 4, and that is already a violation to this rule. Therefore, for a one-to-one function to exist, then A cardinality should be less than or equal to B. However, if you recall our original assumption, so if you recall the assumption, we are assuming that A cardinality is greater than B cardinality. And there exists a one-to-one function from A to B. And this is now a contradiction, and that is exactly caused by these statements. So this is A, cardinality of A is greater than B, but for us to have a one-to-one function from set A to set B, the cardinality of A should be less than or equal to B. This ends up now in a contradiction. Therefore, the original proposition is true. So this is now the pigeonhole principle is proven by contradiction. So that's it.